Hello and welcome to today's Wolfram Institute live stream. Today we'll be doing some live science, reviewing a project that myself, Brian Mboya, and Nick Murzin and Joseph Stocke have been working on for the past couple of months. This is about fluid dynamics on using a cellular automata to run fluid dynamics on a triangular lattice. So this is an example of a gas lattice model. So the overview is like this. This is from a New Kind of Science page, chapter 8, section 4, page 378. So you have a triangular lattice, and then you have particles moving on the vertices, moving along edges of the triangular grid. Each particle moves 1 unit in its direction per step, and there are collision rules for dictating what happens when two or more particles collide. So this is similar to cellular automata update rules. Basically, you have a vertex, you look to its neighbors, you look at the state of its neighbors, and these rules will tell you how to update the center vertex based on the information contained in the vertices around it. So rather than having particles pass through each other when they collide, they'll kind of ping pong at different angles, and that'll add some randomness or stochasticness to the simulation, some rotation. Now it's still true that the number of particles before and after the collision are maintained, and the sum total of the momentum vectors are also maintained. So it's conservation of mass and momentum, but the directionality is sort of ad hoc. This is a deterministic model. Some models will have the angle of the outgoing collision be a randomized choice. So it might be like a 50-50 split between them colliding and then rotating to the right or rotating to the left, for instance. Now, so these particles are moving around on the grid and colliding at will, and then essentially it looks mostly chaotic. So this is kind of what it looks like. Here I started out with a certain density of particles and have them moving around in the grid. The boundary conditions, there's nothing bouncing back. So when a particle exits, it's lost forever. So they kind of bounce around, collide, then get lost. In any case, so when you're zoomed in, there's a lot going on, a lot of chaos. When you zoom out and start taking averages of these vectors, you can get fluid-like vector fields. So here's a simulation where there's a certain density of particles moving around and a certain weighting of a wind, let's say, to the right, so that you have more particles facing rightward than you do other directions. When you take averages, so this is zoomed in from here, this is zoomed in from here, etc. These vectors are taking 5x5 averages and starting to see some smooth out behavior. But when you take larger and larger averages, for instance, 20 by 25 by 25, start seeing that the particles are indeed flowing around this obstacle as they're being as the wind is flowing rightward. Moving the simulation forward on a very large grid. So here, this is setting up a rightward, again, rightward wind, and then an obstacle, taking very large averages of the velocity field. With certain conditions, we get a vortex shedding. I believe it's called a Van Karman vortex street. In any case, the flow behind this obstacle, things are flowing around it and into the low pressure area behind it. And then after some 30,000 steps in this animation simulation, this configuration destabilizes and you get an oscillatory mode where vortices start shutting off. So our project we've been working towards is to recreate this. And this is still working on it. We have not yet recreated these vortex sheets, but we had a lot of progress towards this goal. The closest
Can I ask you a question?
Yes, please.
Can I ask you a question, Dugan?
Mm-hmm.
So you're saying you're trying to like get to this goal, but I'm looking at an image. So are these images created in a different way, or yeah, that's what I was curious
about. No, these images were created in the late 90s, early 2000s for NKS, running on a took about a week, they said, to calculate this to 70,000 steps, or at least a couple days on that on the hardware at the time. This is my best attempt at this. So this is on a much smaller grid, but still taking about 25 by 25 averages. So each vector here represents a block of 25 by 25 vertices on the triangular grid. And here I get a stable low pressure region behind the obstacle. The obstacle here is not shown, not drawn, but it's right here at the left. There is a steady wind coming in from the left side, and on the right side, the boundary condition is that everything just kind of falls off. So this isn't a periodic boundary condition or anything like that. It does take some time. You can kind of see some fluctuations, random fluctuations coming in. The vortex at the top and bottom are growing in length, but it doesn't destabilize and start producing these vortices here. I think what's needed to do that is to expand the region above and below this to allow some movement from side to side, or from up to down, basically.
Isn't that just another way of playing with scale, though? Like in some sense, these averaging regions is just kind of a way of of looking at the system from different scales, right? Am I interpreting that correctly?
It also removes noise because you need to look at the average motion.
Okay, yeah. But it also is a scale thing too, right?
Yeah, well, at the base scale, right? You can't get any finer resolution than the underlying grid.
Yeah, but you could also not really see anything if you're looking at, you're
At
not
these
going to see any
averages.
kind of pattern. Yeah. But no, if you're looking at like individual elements, it's hard to actually even see any kind of pattern like phenomenon because you're just observing individual things. So if you can see, so averaging is sort of bringing things to a more observable scale, it
Hmm.
seems to me. Or maybe I'm just misinterpreting what
Well, it's just getting at the
these.
overall trend of what the particles are doing. But I mean, I agree with you that you do lose information, but the trouble here is that like it's this this region here where the I can kind of see it. It's just remaining straight. I don't know why, and that might be of a issue of viscosity or the Reynolds number. But yeah, maybe we could show some of these other examples. So I ran a lot of experiments messing with boundary conditions. So this is showing the density field, basically the particles themselves. You can see on the right side, everything that scoots off to the right falls off. And so you see a low pressure region here build up. And I have a wind coming in from the left side, uh, pushing everything. And then I stopped the wind, or I decreased the density of the wind. So you see this like pulse move. Um, and it's kind of neat. So you can see the change in density kind of see some rotation a little bit, although it is difficult to see.
Hold on, is that plain, Dugan? It's not plain.
Is it not?
Yeah, it might be a zoom artifact or something, but it's like not actually playing the video. Yeah, we don't see that at all. What is this QuickTime? Oh, VLC. Do you have another
think
player we can try? Oh, it's not playing on my
on
screen.
YouTube it's fine. On YouTube is fine.
Oh, okay. That's so weird. Okay.
Um, what do you mean it's not playing for you? Are you
So
seeing my
on
screen on
OBS,
Zoom?
yeah. So your VLC video, when it
Yeah.
plays on Zoom, it's not actually doing the frame updates. But OBS will show it on YouTube, so that's fine. We just
Well,
can't see
no,
it.
I have OBS looking at it's typing my screen as shown on Zoom.
Okay, well then we need to fix it.
Um,
Do you have another media player?
is it really not playing? I mean, hold on. Can
I
we?
can't see. Can you guys see it?
No,
I can't see anything moving really. It sort of changes
I mean, the
slowly.
frame rate isn't great on Zoom.
Zoom is just trying to be smart, but it's not working.
Maybe try full screen. If you make it full screen, maybe Zoom will activate it as a moving. It will notice it's a moving image. It must be the compression algorithm Zoom's using. Just make it full screen and try again.
Okay,
Like make the video full screen. Yeah.
I did make it full screen. Is it? Okay, who can see
That's
something?
crazy. I can't see it being full screen. Actually, I noticed that earlier. Even when you're moving VLC around, like I can't see it move on your Zoom.
What do you see?
I'll send you a print screen.
Gosh.
Now it's full screen.
Yeah.
That's crazy. It's just blank for me now. I don't know if you guys see that. I think Zoom is doing something very weird. It could
Oh,
be
I
the
see a
compression.
screen. I see a screen with the illustration, sort of
Okay.
surround sound. Yeah.
Do you see the animation though?
It's not moving for me. It's just a still frame.
Yeah, it sort of steps through in big
Big chunks.
chunks.
Okay.
Yeah.
That might be a limitation of my upload, but for me, my Zoom is better than my Zoom experience is.
Try turn your camera off, maybe.
Okay.
It also looks like it's different for each person on the Zoom here.
Gosh.
So it's like piping different frame rates for all of us. But as long as it's on the YouTube, I mean, I guess we can just watch it there. Okay.
Right. So I'm uploading not only my screen to Zoom, OBS is uploading my Zoom to YouTube. And so my upload limit might be a little capped.
Could be that. Yeah, could be that.
Okay.
I guess it's just because of the amount of pixels, the moving pixels here, the compression is like really hard because almost every single pixel in the frame is moving at every frame.
Mhm.
So it's kind of like Zoom can't compress it, which is an interesting computational experiment in itself.
So in the future, we'll measure at entropy by frame rate.
Maybe make the video really small on your screen, then the compression will do less work. Just an idea.
Is that better? That might be better. Not sure.
I'm seeing a new frame about every 4 or 5 seconds.
Oh gosh. Okay, well, I'm seeing it better than that. All right, well, technicalities. On my end, this will go better if someone else shares screen. But, I don't know if anyone's prepared to do that. Joseph, would you be
Well,
interested in Brian?
So, yes, I can do that. I can share uh, the video. Are you talking about the video or the entire
The videos, yeah.
discussion? Oh, so I just have code ready to execute, so maybe we can just run the code and see if it works.
Let's try it out.
Or we can discuss this. We can run the code after the discussion, so that we move. Yeah, I don't know. Let me see. I don't think I have this video. Can you let me try to share.
Yeah, maybe Brian can just talk through the code so long, and then if you can upload those videos onto the Dropbox, then one of us can share. It'll be good to look at kind of the code as well at some point.
Yeah, there are some videos on the Institute on the Discord in the Click to Copy channel. Brian, if you wanted to share screen, go ahead.
Yes, I'm sharing now. Let's try this. Let me know if you see it.
Yes.
Okay. I need to find stuff. I just have code open, and so the video. Okay, so we can just go through the code. I mean, I can show the simulation we have on the channel. If that's
Okay.
like I feel like I'm jumping ahead of I did not know the plan exactly. So for the discussion, as Dugan has already explained, the way that the update rules work and the way that we compute each particles and the state that each particle will be in the next step. So what Dugan was trying to show is like an example of a simulation of how the particles interact with each other and how they end up to finish the updates. So for example, in this simple sim, we have like a few thousand steps and on a grid of 500 by 500. And then we set up everything else. Like, for example, this is so the setup will look like this: a source where the particles will be coming from. So if I run this simulation, we should be able to see like the way the particles updating throughout the steps. I don't know if this is showing what's happening. But,
Yeah.
Uh,
Yeah, that was coming through pretty good.
yeah, so this is like an example of how the updates work. So for example, in this setup, we don't we're not initializing the grid with any particles. We just set up a source. So the source is where the particles will be coming from, and then the update rules just updates each particle. And now you can see how the system shows how the updates happen in real time. So for example, this is the particles coming from the source and then hitting boundary conditions. So so the corners or the edges of the grid are walls. So every particle that hits the wall just bounces back to based on like the rules. I
Mhm.
can show, I think my computer just show something. Let's see what's happening. Can you see something happening?
Yeah, when you run the simulation, you have that video down there. And the source emitted in all 6 directions along the hexagonal grid, underlying grid. And those streams hit the walls and then bounced back.
Yeah, I think let me my computer just hung for some reason. Sorry about that. I'm trying to fix.
Not very healthy for a GPU to screen share and run this one.
I need to.
It's a GPU code, right?
Yes.
Metal
No,
Wolfram.
so I'm running. So this is Wolfram code. I think I have Docker running, so I need to shut it down for. Oh my God.
What's interesting with this research is we're running into the limits of what's like computationally feasible at every step of the way.
Yeah.
So we see it even in just trying to show the research, we have like computational limitations. It's pretty wild.
Yeah, I think it would be interesting to see the updates when it's run on a GPU or something. Okay, so let me try to do this again.
So James, if we did this with a real wave tank with real water, would we run into the computational limits of the actual universe?
Yes, if you try to record every particle movement simultaneously, I think you would.
Um, so maybe ignoring the technical issues for a bit, it seemed like there to my eyes there was a bit more structure than I would have expected, given that it's all ultimately random and there's enough goes that the law of large numbers should kind of homogenize things. If you go back to the
Yeah.
image.
I mean, this is a story of statistical mechanics, right?
Yes.
So yeah, what's
It's
happening in
not quite
reality
so,
is like all these
it's not quite
parts.
so apparent here, but if we
Mhm.
went back to what we were looking at like 2 minutes ago, it was a bit further along in the evolution.
Which one? So maybe I can share that. Right. Are you talking about the image?
Yes, the image. The thing that I was sort of saying is that it's more a question or a comment, or a discussion point. You'd think that, given the amount of averaging you're doing and the size of the grid, you wouldn't see quite so much structure. It's kind of got an amount of structure you'd expect with something more zoomed in. Or maybe it's just my intuition that is off.
I think most of the apparent structure just comes from the way that the particles are being spawned in. When they travel in certain directions, they're not able to interact with each other. They're only able to interact with each other when they're interfacing at a certain angle in order to allow for them to bounce off.
Mm-hmm. Yeah,
Because
they
at
2
each
at a
step, the
time or 3 at a
momentum,
time.
yeah, the momentum in a given small region needs to remain conserved.
Yeah, and the collision rules guarantee that. That at least at every collision, the momentum is conserved as a sum.
Yeah, but there are a number of rules that dictate the motion of the particles
Mhm.
where they necessarily have to phase through each other because doing anything otherwise would mean that momentum is not conserved.
Right.
So you're keeping momentum is conserved because the rules insist on it. Have you done any entropy measurements of any kind?
No, I don't think we have done that. Right now, what we have is just conservation of momentum and I think density. So we haven't gone to entropy yet.
Right. We've just been making density plots and vector plots essentially. Now, that'd be really interesting to take measures of entropy on the data.
What methods are typically used to measure entropy in deterministic systems?
This question keeps coming up, and I think we never have a good answer to it.
I mean, in NKS, Stephen uses like Huffman encode or like different encoding schemes.
I mean, there's the entropy function, which probably does that under the hood.
I mean, it's just number of configurations possible in a configuration space or something like that. Rod-Shannon entropy.
Yeah.
So
I mean, like the entropy of a bit stream, for instance.
I guess what difference does it make that it's deterministic for any of the standard entropy measures? Why would determinism be different? That's cool. That's playing very nicely now, Dugan.
Okay. Okay, so this is amazing.
okay,
Brian.
so
Oh, Brian's
I'm
playing
sharing
it.
the
Okay,
screen.
that
Yeah.
I
makes
don't know
sense.
if I'm sharing the screen. Let me see. Let me try to share again. Can you see it?
Yeah.
Yeah, but you were showing a really fascinating effect and then moved away from it.
Oh,
I think what everybody said, I don't know if everybody agrees, is you had like 3 white blocks that just seem to have emerged.
oh yeah. So what we have here is we have a source of particles, and then we have a rotating optical and a static one. Then we have a sink here. So what the sink does is just let me run this animation. So what the sink does is just gets swallows the particles like a black hole, and the source generates more particles. And oh my God, what's happening with this?
So is the source just constantly generating particles at a fixed speed?
Yeah. We're not like
Right,
deleting
could
the
you consider
particle.
having the source do something more sinusoidal so it'll actually look like waves? Because the thing is, in seeing this, it doesn't really look like there's any sense of constructive or destructive interference.
Mhm.
Well, you
Um,
wouldn't expect that to be typical of a gas source. Typically, you'd think of a gas stream being a source, but then if you want to have some sort of wave effect, then you would have existing particles in the box, and then the source would perturb those particles instead of generating new ones.
But okay, it's correct that I was viewing this as the title of the thing was computational fluid dynamics. So I was kind of thinking of it as more liquid than a gas. But is it the case that you wouldn't get this kinds of interference if you set things up properly in a gas?
Technically, this is a example of a gas lattice model, what it's called. So, gas and liquid is just a measure. The difference being a measure of viscosity or density. So I'm not sure what the difference would be. I guess a gas would just be a less dense fluid.
I guess if you initialize with density and velocity, let's try that. If I do initialize with density, then we'll see the wave-like structure. Let's try this. I don't know if it's the one.
What are you changing this time?
So initial condition, the initial lattice, I initialize particle with some density and velocity.
Uh-huh.
And when you do that, so the initial setup has something to like to run particles with. So what that does is that the particles now collide with each other. So when you have just an empty lattice, then particles just like move to whatever. The only way they collide is when they hit the wall. But when you initialize with different initial conditions, for example, if I initialize with different density values for each particles, then we get this sort of effect happening. Let me try to run this. A wave like forms at the position where the source is.
For the source, can you make it emit in only the 3 directions to the right instead of all 6 directions?
3 directions to the right.
The easiest way to do that would probably be to just add sinks or walls around the source in order to force it to only emit in a certain direction.
Okay, let's try this. So the source you want it to go to. Can you say that again, Dugan?
Right. So instead of the source emitting in all directions, only have it emit in a couple directions.
A couple directions. So like I can turn off a few. So source.
Big cast. I guess it's maybe it was that 128 because it's being
the region.
install
for
region
the source.
compiled function and then install region compiled function. This is the thing, and then the base is 256 times the type.
Yeah, this is just the base, the number that
Okay,
the
so
state of
yeah, what's type 3 then? Type 2.
type. If it's a source, then if it's type source, then we have 3.
Okay, so
And
if type
type-
3, then 127. So that would mean
all the directions. So
I see. So we're looking for like 0, 0, 0, 1, 1, 1 kind of thing, whatever that is in base 2.
Like 7?
Yeah. But I guess
7.
how did we index the directions for the emitter?
The directions. The direction is just all if it's we are looking at a hexagon. So
Yeah.
hexagon, it goes to 6 directions.
Yeah.
So we need to so if you have a circle points, then you get all the directions that you want for the hexagon. So
Is it using exactly the same indexing as the circle points with 6 points?
no, it's not the exact one. You have so there is a set. So the initial way you set up the directions. So I'm using a parity check. So for example, it's hard to configure for a lattice that is a hexagon. It's hard to configure and get the exact structure you want for particles to move. So you have to figure out some other way to make it look to make particles operate on a hexagon. So so if you have a hexagon points, let's try.
Like you could just you could just say point at circle points. No, you can point will automatic. Okay, whoops.
It needs to be inside of the graphics because you're drawing 6 different graphics objects.
Yeah.
Okay, so each particle, like it will operate on such a hexagon. So what you'll get for if you have a setup like every particle in a grid, then you get a triangular setup, but then you want particles to operate on a hexagon. So to configure that, you need to figure out, okay, we're using rows. So each rows gets you which rows to, for example, if you want to have one row that has particles in a grid, or sorry, I'm confused here. So let me try to run this.
Right. So the if it the way that the vectors were listed.
Here. Okay, so what I'm trying to explain is this exact thing here. So if you look at this, each particles in this grid, it's formed in a hexagon structure. But when you initialize a grid, you'll have a triangular structure. Let's try to do an example. So for example, if you have table of points,
I'll share screen for this because I had this
Yes.
prepped. So you can keep sharing your screen, Brian, but I'm showing
Okay.
the audience my screen right now, and yeah, so there's a couple different ways to index the points of a triangular lattice. Can everyone see like what's going on my screen? Is that coming through? Hopefully, who knows? All right. Well, anyway, the first method I was thinking about was you could take a square lattice of index values. You can map a square lattice onto a triangular grid directly using a linear transformation. So it's kind of a skewed transformation, and then this will do it. And this is kind of simple. However, there's a caveat in the sense that you get like a trapezoidal, not a trapezoid, but a rhombic, a skewed square of values. So if you want to render like a rectangular square on the plane, you would have to have an index. It would mess up with your indexing. You'd have regions of your index space unused in the final thing. So a better way to do it would be to stagger your rows and columns, or columns basically. Basically, you take every other column and you push them upwards a certain amount, and then you can get to a triangular lattice where every point is surrounded by 6 others. Okay. Is that what you're getting at, Brian?
Yes, that's exactly what I was trying to explain. Thank you, Dugan.
All right. And then, yeah, so luckily we are not having to index the vertices of the hexagonal grid, because that would take 2 different copies of the square index.
Yeah, and then to get the particles exactly in the grid that we want,
Mhm.
that's also a problem. So you have to figure out another way. Since we're using bit operation, then you have to figure out another way how to get those particles in the order or in the grid that you want.
Precisely. And then,
And for
yeah,
this,
so
we used, sorry.
yeah, and then I guess the directionality for the source. So you have every point has 6 vectors coming out of it, and there's a certain ordering to what we did there. So it looked like if we were using circle points, it was starting at the top and working counterclockwise from the top.
Yes, so for our case, the source, if the source is 127, then you get
Yeah, so if I want to emit along these directions 5 and 6, then I want to turn on these 2 indexes. So we're yeah, so 111 equals 127 in base 2. I guess if we're looking at having the 5th and 6th positions being turned on, then we're looking at 3 in base 2. So we can try that.
Although I have some contentions about whether this is the most natural indexing scheme to use in this system.
Right. So yeah, we so what other indexing schemes would be good?
My work was directly at the fluid element level, and so there's a certain embedding that you can do directly onto a square grid from the true positions of the fluid elements that encodes both their position on the triangular grid and their direction.
Right. So that's. Do you want to share screen and present? Talk about your summer school project, if you want.
Yeah, I can take a crack at it.
Okay.
So it's possible to take the triangular grid, and you can notice that well, each edge on this grid is associated with 2 fluid elements, and then you can impose a rectangular lattice on top of it in such a way that each cell on the rectangular lattice is associated with a fluid element from the triangular lattice. And from there, you can use this new lattice to construct a scheme for writing the automaton as a block cellular automaton.
I see. So you have one square index, one square on that grid, being responsible for containing information about. Okay, so let me see if I can.
Yeah, and so this just
Okay,
results
so I
in
have like
a
we have this
really-
vertex here, and like its outgoing right vector is contained in this box,
exactly.
and
But
then
now there's a certain question about how exactly you're imposing the rules that dictate how the automata moves. And so the position, the velocity that a fluid element has is going to depend both on its position and the time step, because there are 2 alternate time steps.
right, you had a transport time step, and then like a collision resolution time step, if I remember
Yes,
correctly.
and so on collision steps, the kernel looks at the typical node that you would look at on the triangular grid, where the fluid elements are coming together and meeting at the center, and you can pretty much directly apply the collision logic at these kernels. But then at the transport step, you need to consider pairs of fluid elements and say, well, these fluid elements need to be transported past each other.
Mm-hmm.
And then there's a certain way in which you can take 3 pairs and pack them together into the same kernel as the collision step, just offset slightly.
Right. Yeah, no, it's interesting that um, 2 particles coming out of each other might not bounce off each other. That is to say,
Well, that's already done implicitly in the original writing of the automaton. It's just that you're not considering these 2 steps differently. I believe that the original logic, I'm not sure if I've seen the exact reproduction of the original logic, but other people have reproduced it. And typically, what they do is they look at the vertices on the triangular lattice and then they say, well, we're going to apply a cellular automaton rule that looks at the adjacent vertices and says, well, given these adjacent vertices, what are going to be the new inbound fluid elements, and what effect does that have on the outbound fluid elements from the original vertex? But really all that's doing is packing these 2 steps together when they can be separated, and it results in a simpler model.
yeah. Or yeah, it's just there's a lot of different ways to like code this up. But ooh. Is
I
that
hope
this?
that looks nice on your screen, but here you can see this is the underlying grid as it's being evaluated, and then on top of that we can apply the visualization to bring that back up to the triangular lattice. And then I run into similar problems with the boundary conditions in the sources and the sinks, and I don't believe that my approach is as developed, but it would follow similar guidelines as to your work.
Can you hold frame on one of those grids, the blank ones? Further up, just a triangular grid.
The
White.
meshes, is there a specific
Just the
mesh you want
mesh,
to look
yeah.
at?
The one that's white. I want to draw something.
This one?
Yeah. Okay, so say that there's a particle here, and then a particle here. And then in the next step, I'll use a different color here. The next step, can I erase something?
But you should take note that on the transport steps, the fluid elements are always facing outbound from the vertices, but on the collision steps, the fluid elements are always inbound into the vertices.
Joseph, are you encoding all of that in the rules? For example, we do encode the boundary conditions in the rules, in our rules. So I'm curious about what your rules look like, though.
I think the boundary conditions were fairly straightforward because for walls, you can just say, well, don't update. And when you don't update on either the collision step or the transport step, then that results in it effectively bouncing off of the wall. But it gets a little bit more complicated for sources to make sure that it's all traveling in the direction that you want it to travel in. For sinks, I believe
Right.
you can just say remove the fluid elements when they come onto this region, and that'll just act as a sink.
Yeah.
Yeah, so the point I was making, I'll change sides here. Okay, so if this red one and this blue one are in this configuration, then at the next time step, the idea is that they both hit this vertex and then collide. So, but they also like collide and bounce off at an angle. So you get this kind of thing in the next time step. But if they're offset, like this, then in the next time step, the red one goes here, and the blue one goes here. And then, since they don't hit the same vertex at a particular time, and in between, there's no vertex in between them, the next time step is the blue one goes here, and the red one goes over there. And so even though that they're coming on trajectories that would collide, they don't actually. So half the time they do, half the time they don't, depending on if they're an even number of steps apart or an odd number of steps apart.
Yeah, but that's a constraint of the geometry of the mesh and the fact that we
Yeah.
impose local constraints on the motion of particles.
Mm-hmm. In any case, yeah. So, okay, I see. Now scroll down. So what are we looking at here? We're looking at the individual components of your square array.
Yes, I'm taking the square array, which is like this Boolean array, and
Mhm.
you can draw this with array plot, and by transforming it, because initially it has the incorrect aspect ratio, so you need to
Oh, yeah.
squash it a little bit, but then it'll perfectly line up with this triangular grid, and you can see how the underlying lattice where the computation is done can be visualized here up to the triangular grid.
Right. So the outgoing direction here on this vertex is being occupied by this square.
Actually, that's two cells. There's the cell at the top and the cell beneath it. So there's one fluid element that's exiting to the left, and then there's one exiting to the top. I'm sorry, to the right, and then one exiting to the top right.
I see. So this is the diagonal, and then this is the. I see it. Okay. And then this one is the downward.
Exactly.
Got it. Super clever.
Thank you.
All right. Brian, were you able to get the directionality on that source sorted out?
Yeah, let me share my screen again. Yeah, set it to 3.
Mm-hmm.
But I just run this again. Still getting the same.
Did you recompile that function though with the 3 in it?
Still get the same.
Hmm.
It's taking so much compute power. We'll try 0, then we should see ourselves.
Are you recompiling all the functions that are being used in the tech stack? Because sometimes if it's a compiled function that you're using to run this, then if it's referencing another compiled
Oh,
function, I think it needs to compile up.
right. So metal simulate, is that a compiled function?
No. I don't know why it's not updating. I'm running the wrong. Let's try here. Okay, still.
You might also need to clear the symbol if it's being assigned to a symbol.
So it's not assigned to symbol. Let's see now. So taking out the source, then I need to figure out why it's not updating. Set it to 0.
It's being assigned to the symbol install region compiled in place.
No. This?
Yeah, you might need to clear that and rerun it.
No, you don't. Just a single symbol definition doesn't have to be cleared.
See if that works. Okay, that worked. Actually. So let's set it to 3. need to clear again, I think.
I think it was just that it was commented out in the other function, and maybe that hasn't been updated yet.
Yeah, let's try it. No. It's calling it in the other function. No, this is using a different one. So I need to call this again. Okay, now that works.
Oh, I see. Well, there seems to be the initialization. I think worked, but when it's simulating, it's pushing in all directions.
Yeah, because the other particles come in the way at some. So it has to like also encounter put the other particles in its update.
Is it still encountering particles like that inside of the sink? Because it is all black. I think it's still emitting from all sides.
The first frame looked correct because it wasn't all black; it was dark gray, which means it was just 2 out of the 6. And then when it started to go update, so there might be like, I'm not sure what's going on.
I think oh, I see. So the update array must be, let me just check that. It must be still updating. So what the metal code does is the text the algorithm in this function that update the update algorithm and then does the updates. So, Nick, if I change something here, then because I'm not using metal, then I suppose it won't work, right?
Where do you want to change? Change what?
Update array. So the update
In
array.
the code for that. I
The
think usually if you change it, you need to restart the kernel because it's somehow, if you load the library, it gets burnt in. You have to restart the kernel.
I see, because we still have 2127 here, so that's why. Okay. Let me try 3 and see if this works. Oh. I'm gonna have to shut down the kernel again.
Just don't forget to recompile it.
Right, okay.
Need to run that command line.
This Yeah. Thanks. And this is the output. It's still running. Look, some stuff still running. Yeah. So it's done. Try this. No.
Oh, poof.
Did I do this? Try this. Zero density. Okay, I don't think it's updated. Yeah. Okay, so
But all that's
that's
commented
what
out, though. I mean, why is it red?
it's a source.
I see.
Text
Oh,
in the
I
source
get it.
code.
Wait.
Yeah,
Type
didn't
equals right,
change.
so that has to be 3.
Yeah, I don't know why.
Did
I
it not
thought I
say?
changed. Yeah, I mean, let me try. Let me find out why it did not change. Where am I? Okay, so it's fine. And
And that got exported.
yeah, hopefully it works. The problem with this, I have to shut down the kernel and then try again.
Hmm.
Let me see if this is without that. No. Oh,
Did it overwrite
it
it?
doesn't.
It overwrite it.
Yeah,
Push it back.
I wonder why that is.
Oh, wait. Export file name, and then it's inside that iconized thing.
Oh, Oh, I see.
Okay, so
That's crazy.
there's a 127 here towards the bottom that
Well, you don't have to run this export if you use the command line.
Yeah,
Right? You add one or another, yeah. You can remove that export thing. It's confusing. If you use just the source code.
so
Oh,
when I
wait a
change that,
minute.
it's right.
what? So this export thing is overwriting that file, which is being piped into the source elsewhere, right? So if you edit it here and don't export it again, or we could do this.
Let's try changing this.
You just don't export anymore. You already have it stored, right? So change in the text editor, remove that export and keep it there.
Yeah, you can comment this export line out.
I'm trying to export again. I see.
Okay.
Let's change this. Okay, I need to shut down the kernel. That's find anything that I'm not using. Bundles. Yeah, this is a lot. I mean, if you wanted to do these experiments, then a better way is to have a way to change those values directly.
Cross. Okay, so here it's loading the functions from the metal library.
So we load the functions.
Or in function load. I'm just wondering what it's doing right now. Oh, it's done. Run it.
Oh yeah,
Ah,
that worked. Okay, let's get back. Let's get back our density. But this is doing a random initialization
Mhm.
based on those density values. So if you do that, and if,
Mm.
um, how it starts. Yeah, it's hard to tell what's going on unless we plot the fields.
The vector fields.
Yeah. So velocity and so history. Right. History. What do you get from simulate history? Yes, do the last one. Yeah, that's bad. My data.
Oh, data, sure. Oh, hell. Oh, it's still running though.
It's crashed. Okay. Oh wait, it crashed everything.
In a way, that's good because I kind of want to change which directions. Like I was hoping everything would go to the right, but the way everything the way it's indexed it went to the left. So I think we need
Yeah.
to say like instead of 0, 0, 0, 0, 1, 1. We need 0, 1, 1, 0, 0, 0 to get the opposite directions, and that would be
To the right.
yeah, the two rightward directions. So I had the encoding wrong. So the IP type 3, 3, we need
3 you need. So for 3 it's going to the left. So that makes
16 plus 8. 24.
a lot of stuff to compile.
Yeah.
So this goes to the left, and we need 1, 1, 0, 0, 0, 0 to go to the right.
I think 0, 1, 1, 0, 0, 0.
0, 1, 1, 0, 0. What number is that? So
24, I believe.
0, 1, 0. No way. It's 24. Let's try that. 24. To be I want to comment whatever I'm not using now. So it doesn't compile. else? Oh, everything here. Okay. Shut down. No.
Would that one be changed as well?
All right. Which one this?
Yeah.
Okay, yeah. Maybe not, because they are.
Is that just for the first
Yeah.
frame?
Yeah, for the initial,
Mm.
for the set.
Okay.
But let me try this 24. Let's see. Oh, look up, look up, look up. Look up 2. Which here? I look up.
Oh.
There you are. I lost lookup.
Grand block.
I saw it somewhere. Oh. Yeah. see if it works. No. Okay, we don't want any crash. So just this way. And let's change.
Was data to initialize to an empty set?
John?
Data
Data?
to.
List.
Oh, I see. Okay.
And
Well, anyway,
this is data one.
we're not using it, so we can
Okay.
skip it. Let's see if this works. Oh no.
So I need something. Oh no, data one. Oh, that's why. Okay. So this should be. I can just get this back because I think I was passing in the wrong. Still to the.
Oh,
That's bad. Did I not do an update? Oh, I see. I didn't do an. I didn't run this command.
oh, I see.
I need to call it fast.
Oh, it's still doing the simulation.
Yeah, let me cancel this.
Yeah.
Okay, hopefully it goes to the right. Um,
Hmm.
no. Okay.
Did this one get recompiled?
It's 2-0.
Yes. Cool. And it hits the blocks. The blocks
Yeah.
make it go spinning. And then, yeah. Let's see what happens with we have that density in the initial settings. So get the shock wave coming off the jets. And what's the size of the array?
1000 by 500.
Okay. Wow.
Yeah, if you go higher than this, will break. No. Okay, let's see if the source is still emitting itself. The last one was this. I wonder if I can do it. What's the dimension? What? Oh, it's the image. I need the data. Okay, so fields. Let's see how the fields look like. So I need to compute mass. This works, will work, which let's try velocity data and it works.
Oh. So it's data the whole history. So you're just like taking the
No,
last frame.
last one. Yeah, the last one. Array pod should be array. So this is numeric array. How do you convert this to
Maybe normal.
yeah. Is it to array? Sparse or not?
So it's a typed data object.
It's a numeric array, but this expects just a list.
Do normal. Need normal.
Normal.
Mm-hmm.
Oh, sure. Yeah. Okay, so we have velocity. And we can plot these two. Okay, nothing happened. What is this? Transpose. Okay, it's not good. So let's try. This is 25. It's huge.
Mm-hmm. Just looked like it was taking longer to render because it was 5 times as dense.
They're too small.
Let's see. So it's making a graphics, right? Or what
Yeah.
is? Oh, the vector scale is 0.001. So we can increase. There we go.
But I think I need to add 25. I see.
Try 10 or
Estimate.
something.
10.
Okay, so here's the thing. All right, it looks like there's a little bit of an error in the way that this is happening because the section coming off to the top right of the source should all be pointing to the top right, and so that
So
the
the
vectors are like indexed incorrectly in the visualization, but it executed pretty well. So I'm like really happy about the subroutine. It's just the way that the directions are calculated. So
Yeah.
backwards or something.
So I think this is the source. Okay, so the calculation must be wrong. Getting the center. . initially what happened.
You're gonna want to say x goes from 1 to length data, comma 1 instead of delta 1. Otherwise, it won't index correctly. X comma 1 comma length data comma 1.
X.
X comma 1 comma length data comma 1. So an extra comma 1 at the end to set up a.
It's too fast.
What's the 0.3 mean? That scaling the velocity vectors as drawn?
The arrows,
Uh huh.
the particle, scaling the particles. So Dugan, you think we should where is it? We should probably calculate better fields.
Something was wrong
Where
with
we-
visualized velocity. So the indexing was mismatched on the either calculating the velocity field or visualizing it. And so I don't know where the. So you're in experiments chapter 8 section B6W-3. I think he sent me this file.
Mhm.
Okay, so let me look at it. And then send the visualized velocity. So vector plot. So in visualized velocity, that's I don't know where you define your vectors, your hexagonal vectors.
I don't have them.
Oh, calculate average velocity. Okay, hold on.
For the visualized velocity. I think you
Or it's
just define them again, because I don't have it for the visualized velocity. Vectors for that.
Right. So it looks like the okay. So the V field is a transpose of the input. So what is input here is like already um, the data
Transpose,
being
yeah.
vectorized, and the compute average velocity function uses the compute mass function, and the compute mass function has vectors assigned to the circle points. Um, and circle points has everything starting from the top and going counterclockwise from the north position.
So when I compute mass, I do the same. I use the same vectors
Um,
going to the from I think right.
right. So okay. So this circle points goes in a counterclockwise orientation, starting from the north, and
Mhm.
um, I'm not sure how you encoded your bit masking schema, and like it might be if you say
So if I have
if
a
you
few,
reverse the circle points, it might help.
so what I have is how I'm encoding the bits is so this point will be on the north side,
Mm-hmm.
then going clockwise,
Okay.
right?
Yeah. So let's try this. Where it says
Thus,
reverse the vectors for compute mass.
okay, well. Okay.
Okay. Good. So it looks like where that source is, it's computing it. Okay, so let's get another frame down the line. Go to like frame 100 or something.
7, okay, I see. Let's try the last one.
Oh,
This is the last frame, so
let's try frame 50. Um,
be nice to play this. Okay, let's see if
hmm. Let's set the density initially to 0 so that we can get rid of the noise.
Yeah, something boundary conditions. I think we lose particles. My boundary condition isn't working.
Oh, interesting. Oh, hold on. Reversing reverses the orientation of how
The direct.
yeah, but it also starts at the position 6. Like we need position 1, 6, but we need to rotate right. So like reverse and then rotate right that list. Yeah, so rotate right on reverse on the circle points. Yeah, like that. Now try. Yeah. Oh gosh. Okay. So what happened? What happened? That didn't work. It works for the.
You need to reverse it, rotate again.
Mm,
Where do we want them to go? So the direction. Hmm. Rotate and reverse.
wait a minute. Wait a minute. Reverse.
No, it's not.
Hit one of the earlier frames. Hmm.
I think it's the other way around. 110101.
Um, huh.
So
Guess you could use map indexed. Does. But you're trying to like say like um, here, try this. Trying to see which index corresponds. There you go.
Beats.
If you want to make the letters bigger, you can style the indexed. No. Okay, yeah.
So each bit goes. Okay, it's wrong. Starting from this point. And so this should start from here and then go clockwise.
Okay, so that's where the reverse circle points comes into play. Yes.
Yeah. Compute mass vectors. Vectors I'm doing a dot in bits.
Oh wait, hold on. Compute block mass. And the vectors here are
These vectors.
they right, bits dot vectors. Right, that's okay. So the bits is what, like an array or a list? It's like that.
Incoming. Yep. And we can do vects on these to get this.
Right, okay. So if the the vex is the circle points.
This is what happens, yeah.
So the reverse rotate right of circle points does start at the top and go clockwise from there. And if we do a bit,
Reverse. So reverse this. Get this. And so this. I need to do something with this.
I pasted in chat for vex using the
index. Text coordinates. No, okay, so I think I had this.
Oh.
I want to know how the encoding is done. So it's the direction. I know the direction of each vectors. Sorry, I know each point in the hexagon where the bits are, but not how these vectors is computed. So if we are going from left to right, then the vectors should be
So what bits is reversed? Or
this. No, this is not reversed.
yeah.
Okay, so the mapping. Let me check the mapping. Okay, so no, where it's so at each point, calculate the position and then get the bit for that. So if I'm doing quotient of t. So say this is I. 53. Okay. Get a 1, so it's not reversed.
What's not reversed?
The bits.
Right. Right. So the um
So I guess it's my visualize function that isn't doing the right thing.
uh
Yeah, this is the wrong code. Visualize function doesn't really. Center.
I mean that's probably correct where the center is.
Mhm.
And it's getting the velocity from I mean one thing that is true is like you're going from the center and then subtracting and going from the center and adding. So like you can really just start from the center and go center comma center plus velocity times scale when you make the line. I
The
think
scaling.
time scale.
I mean, your time scale.
Right. And so that make all the lines drawn half the size. Okay. And
Just do.
oh, I see it. It draws like little points for zero vectors. But that's all right. Anyway, so
Okay.
and the v field is coming from the transpose of velocity, and the velocity is a a three-dimensional array. It's like an n by m by 2.
No, 2. It's 2. I think 2. Let's find out. It's 3.
Yeah.
Well, n by n.
So this is with everything like averaged already. So
Yes. So computed from the average velocity. So
and that's
this.
compute block mass that's being used.
Yeah.
So the bit and then the quotient and the bit and is the bits. So that's getting the block.
Yeah, it's getting the bits around the point you're considering. So
Mhm.
the neighbors, the incoming bits. So for each block, so the block is
So the block is coming in as what type of data type?
yeah.
Integer. As an array of integers. Okay, so you're having like
So this is padded based on the size. So if you pass in the block size, it takes a block of the entire grid. And that's passed to these as a 2 by 2.
Mhm.
And then the data vectors. So what I'm getting here is velocity, the loop goes through the block each point and calculates their neighbors. So this is the neighboring particles, the incoming.
So the
And
block is an integer, and the first 6 bits of that integer, that's what your bit anding 127 to get.
yeah, so 127 just tells me how many are they. So the and bit and, if I do bit and 43 and 127, I just get 43. 7.
Right.
So
And,
just
but then you had like the block, it's encoding, it's 6 bits, right, for the particle state, and then are there more bits after that for like this is a wall or this is a source or sink or something like that?
no, I just care about the bits that are surrounding the point. So each point
Yeah.
in the block, I just care about the surrounding bits, 6 of them. And then I'll calculate on those bits, I'll calculate the total density. I mean, the total number of bits, that is the density. And then I'll compute momentum. So momentum, just use the dot function on the bits plus the vectors. And I do that all the time, all of the steps, the block size, dimension of the block. So so if you, for example, if we have let me see if block if you have a something like this constant array of zeros, 2 or 10. And then we do a block of, we get a block of that.
Yeah, yeah.
Block. Oops. What how block works. Function. So if
I understand it's like a kernel kind of moving past. I get that. So I understand like what a block is. But you're taking you're adding up, you're going through each element of this block, and that's what the do loop is for. X for X bound and Y for Y bound. And then you're taking the X and Y index of the block and getting an integer out. And so the integer, we're using an integer encoding to not only hold the state of a vertex in the simulation, how many of the 6 positions are being occupied by particles. Is there okay, so wait, here's a question. So is the table meant to be, oh, I see, you have 2 to the I minus 1. Yeah, right. So it goes from like position 0 to position 5, 2 to the 5th. Right. So okay, so it's doing binary arithmetic on that integer. But is the integer at the block at the extracted integer, like, because you're using more than just 6 bits, right? You had like extra bits at the end that encoded for the type of vertex that is supposed to be simulated there.
yeah, that's why we have like I select those that I care about. So if I'm encoding I'm encoding the type plus the parity and then plus state. So if I have a type of 3, then I'll be and parity is an odd number. So I'm using 0 or 1 for parity, and then state 3. So this is the state that I pass into this.
Okay, so
right?
So the state is on. So you have for the type. How many bits encode the type of the vertex? Is it just normal empty space versus a wall? Oh no, but you had like type 1, type 2, type 3 was a source, and type 4.
Yeah, bits.
Okay, so you have 2 bits for the type, 1 bit for the parity, and then 6 bits for the state.
Yeah.
And so this is a 6 plus 2 plus 1.
So,
basically 9 bits are being used, right? So we have.
Yeah, and we know that from our state is from the rightmost bit, right? So is it leftmost? So we're going from leftmost bit to the rightmost bit. So if I know 43 is on the right side, I'll just pick that pick every bit from the left. Oh, sorry, from the right going to the left. And if I get to 6, then I know that I've picked my state. from this state. So if I'm encoding state like this, then 43 will be how many bits are those? 6. So so what this does is going through 47, which gives us see 47. Okay, so this should not be, it should be 6. I should do 47 plus 3 plus 1 plus 57. So this is what we get. So this is the state, the entire state. So parity, I'm going from left, from right to left using this. So pick this bit, this bit, up to 6, the 6th bit. And that gives me the all the bits, the surrounding bits for that point.
Yeah. Okay.
And quotient is a good way to just go. Oh, so quotient is just you can use bit shift left,
Uh-huh.
which quotient does the same thing. But since we are compiling this, then when I compile, it's not a compile function. Shift left. Six. Shift right. Keep doing that until you hit the 6th point. Anyway, so the problem here is what we get from this, right? So if you get a different, if you get a different trajectory, so if you're going from clockwise, the bits are going from clockwise, sorry, bits are going clockwise and your vectors is going the other direction, then you get a different output for momentum. I think that's where we might be going wrong here. Okay, if I try, because we only have how many blocks are they? Let me see data. Okay, no.
Feel like it's gonna echo a lot of stuff at us.
Maybe I should do mod.
Oh, I see.
5. Hopefully did I
Well,
do?
no, you have to. Oh, yeah. It's the blocks might not be 100. Okay, let's try that. All right, 0. Okay. Oh boy.
Getting so many. I just let me try a small number, large number, but small. Okay, so this is 550, and we go to the last point. Use the last one. Okay, how many are they?
Oh, because the block sizes aren't 50. The block sizes are 10, right? And there are like thousands of blocks.
Ah, I see.
Also, is data ever used in this?
Yes. No. Yes, I
Oh,
think no. Yeah, I don't think so. So this is not being used.
interesting.
Yeah, I don't think we need data here. So it's only being used in mass. Just want to get an example of a state example. It's just zeros. Okay, this is bad. But why not just do
Need to close the echo right there.
block map? Where is block? Oh, this. Size.
Map
I
thread.
see.
Oh, length to specified block size.
Yeah. Oh, I see. Hmm. Okay, so this is the state.
Okay.
State.
So the largest state that we have is like, what's the maximum of data?
The maximum of
Like it's up to 512, right? Is that what we're looking at?
the dimension of data. Are you
No, I mean, I just mean those values, 256, 384, kind of thing.
oh yeah. So the maximum will be two, is it 17 what?
So we have,
Let's do the math. So if you have integer, oh, no. Three, my wall state types, how many types are they? We have 1, 2, 3. So the four is the largest type. So 4, and then 1. Then we have 1, 2, 7. Should be base 2.
right, so you have 2 bits for this type, 1 bit for the parity, and then 6 for the particles.
Mhm.
So the
Bits,
they had 256 a lot in that output.
256.
And that means
Oh yes,
type
56 is the wall, the space.
empty space. Okay, so
256 is an empty space. So space because of zeros, and then
yeah.
parity is 0, and then this is 2. So 2 means space. Type 2. Yeah, type 2 is a wall. Sorry. So 256 is a wall.
Uh-huh. And then our sum, okay. And then 384 means it's a type 3, a source.
Mhm.
Are there 447s in there, or sources that are filled up?
Sources, yes. How many are there? Let me see. So this, how many sources are there filled up? 2, just 2. I can't tell from this. So
But that would mean that that's the source generating all that output. Now, what's the code for empty space?
Empty set, it's just one.
Okay, so
Yeah.
0, 1 in the first two bits.
This will be an empty space.
0, 1, okay. And then the third bit is for parity,
Yeah.
and then the remaining 6 are for the particles.
Yes.
Okay. So this would mean an empty space on like parity 0 column or row with particles in position 1, 3, 5, and 6.
Mhm.
So particles going north, southeast, southwest, and northwest. Something like that.
But then you have to, do you have to reverse? No, yeah, I think so, yeah. So there will be north. This is southeast. Southeast, yeah. Okay, so if we get this as space, see what this does. Where is it? Bit kernel. So bit kernel takes in X, Y, Z, and X, Y, Z is don't remember what this is. Let me see. I see type and parity and state. So bit kernel would do what we have here. Three. The 3, 2, 1. T. So the kernel just creates a state, a lookup state thing, and so what you just need to do is at the north side there's no particle coming through because is it north or south? North, yeah.
Bit state kernel. 43.
43 is the state, and and the type, which is space, and parity is 0. So index 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, and 2, 3, 4, and 6. 1, 2. Yeah, this could be wrong. One, 0, 1. But I think we are over time. When
Yeah, we've been going for about 3 hours, but
yeah, okay, so the end goal is to make sure this is working, right? The velocity, the
yeah,
plot.
yeah. I think we can table that for the next
Yeah.
some other time. But amazing work on getting the GPU implementation going, because the fact that you could set up a situation, an initial condition, sources and sinks, and then have it run a simulation for thousands of frames in real time, essentially, like right in front of us. Like it just takes a matter of seconds. I mean, we've been dealing with a lot less. Like in my code, which is not GPU optimized, it was, like 200 by 300 grid was updating like 1 second per frame.
Mm-hmm.
And then getting a larger grid was becoming intractable. So this is marvelous. There's just some bugs to work out.
Yeah.
And then
A lot of the compute, a lot of the speed up came from using bit manipulation.
yeah,
So if you run the actual Wolfram code, you get like it runs at least faster, but if you do GPU run, then it's much faster than the Wolfram code.
mhm.
So yeah, so the bit operation was really helpful in speeding this up. And then running this on GPU. So the goal now is to actually simulate this on a large compute, so that we can do like more steps after like we fix all the bugs.
Yeah,
So, like, yeah, but yeah, it should be very fast and interesting to watch.
absolutely. Very exciting. Thank you, Joseph, and thank you, Brian and Nick, for all your work on this project.
Of course, and thank you, Dugan. I think you've done quite a lot too. You helped me during the summer school.
That was my pleasure. All right, let's close down the live stream. Thanks for everyone tuning in. And congratulations to anyone who's made it this far.